Hi, my name's Robert Falbo. Back before computers and calculators, when I was just a young kid, I developed a way to find prime numbers relatively quickly and easily, using a simple equation, 6x times y plus x plus y. By making a giant grid and calculating those numbers out, I was able to find what I'd call seeds. These seeds, when plugged into the equation, 6 times the seed plus 1, would not give me a prime number. Any number that wasn't one of these seeds that came up on this graph generated a prime number. So it was really quickly to eliminate all of the bad seeds, so to say, and generate prime numbers rather quickly. So let me show you exactly how this comes to play in modern computers with binary memory, which makes this a vastly efficient and quick way to generate prime numbers. Although you can't predict prime numbers directly, you certainly can predict all the non-prime numbers, and by process of elimination, that's what you have left. The example below are seeds, and the ones marked yellow are seeds that have been. Anything left over produces a prime. We start by creating two 34 megabit files. That's bit, not bytes, which comes out to about 4 bytes per file, or 8 bytes total. So this total array is less than the size of a 10 megapixel picture, yet large enough to find all the prime numbers up to 200 million. After the array is created, we clear the bits. This takes about 15 seconds to clear 34 million bits. For both the N array and the P array, there will be two passes at a starting point and a step. These values are found in the chart shown above. There are 6x squared for the start of the N array, and then there's 6x squared minus 2x for the start of the array at one level, and 6x plus 2x for the start of the positive array at the higher level. You only have to complete 2,400 levels to find all the prime numbers up to 200 million. For the N array, we can see that the start point is 6x squared, and in this case, for x equals 1, we've got just a starting point of 6. There are two steps, 6x plus 1, 6x minus 1, which is both 5 and 7. So we'll start at 6, and then we'll go 5. So we'll set 11, 16, 21, 26, 31 on up, and we 6 and make steps of 7, so 6, 13, 20, 27, and on up. So we'll do that for the N array first. The array, we start at 6x minus 2 with a step of 6 minus 1. 6x squared plus 2x with a step of 6x plus 1. And you can see that as highlighted in yellow, you can see how we make these steps of every 5, with the N starting at 6, and so forth. And the P thing, we see that it starts with 4 and goes 4, 9, 14, and so forth. If you notice, the red lines show the steps of 7. They also hit 0.6 for the N array and go up 13, 20, and so forth. And on the P array, it starts at 8 and goes on up to 15, 22, as shown below. We now move on to the second level of the sieve. As we can see, 6x squared is going to be 24, where 6x squared minus 2x will be 20, and 6x squared plus 2x will be 28. These will be the start points, and the steps now are 11 and 13. So we'll see how that affects the array. You can see at level 2 how we're setting every 11th bit and every 13th bit of both the N and the P array from their start position. These steps of 11 and 13 all the way to the end of both the N and the P array. If you notice, the other bits that are set 1, those are the ones that were set previously by the 5 and 7 steps. Moving on to level 3, see that the start point for the N array is 4, or step 17 is 48. So it gets us till we get to the end array. We can see how the step of 17, which are highlighted in yellow, continue on up, and the step of 19, which are the red line, are steps of every 19. 4 is where it gets interesting. Because the P bit is set to 1, we actually get to skip the stepping of 25, or 6x plus 1, which is... Before we actually set the bits for level 4, let's look at the array. As we can see, values of 1 are set where the red line indicates, which would be our 25. Those values were actually set during the first level when we were making every 5. This is just 5 squared, so those bits are already set, and then we need to go ahead and continue doing 25. Comparing the before and after of the level process, we can see that only the step 23s were set. Step 25s had already been set previously by the step 5 module. Being able to sieve when the bit value is 1 saves a lot of time. As you can see, the density of as we go along. Also, the exponent value start increases, so our start is going further and further along in the thing. The linear dwindle as much as the exponential value of the start bit. In this process till we get to level 2380. That's pointing to the very end of the array, and you only get one step in the 6x minus 1. You get one step of a value of 14,204, and you're at the end of the array. So it only takes a few to go through. It took me about just under 55 seconds or so to 2,700, and they're shown. Looking at the end of our 34 million bit array, we can see values that are set to 0. Those represent prime numbers, as shown in the red letters, which is actually 6x minus 1 or 6x plus 1, depending on whether it's the N array or the P array, and those values are prime, as shown. If we wanted to find primes around 100 million, we would set our pointer to 1/6 of that, which is about 16,666,667. You can see where the values are set to 1 or 0, indicating whether they're prime or not prime. Again, if the n bit is prime, and that's the ones that I have highlighted in red, the black numbers are non-primes, which are the ones that we found. Primes up to a million, just a minute. Print out those primes takes a long time. So they're stuck in array and instantly for any range, but that is going to take you a lot longer than a minute. One thing arrays and P arrays is go back, and the next video coming up soon.